Let's talk about linear program duality. Suppose I have some maximization LP, right? And here we're gonna have a optimal solution of Z star. Well, let's think about this. We know, suppose we have an Z star and we have an upper bound solution of Z of U. So how can we verify that Z star? Let's verify that Z star is optimal. So every linear program is going to have a dual linear program. And the dual linear program is going to optimize over the upper bound of Z star. So in this case, we're going to want to minimize the Z. Because if we know the minimum upper bound of our linear program is equal to the optimal solution we found in the primal LP, then the Z star has to be the optimal solution, right? Because we know that, okay, so if this is satisfied, Z star is less than or equal to Z of the upper bound, and Z of upper bound can only be, the smallest upper bound is Z optimal, right? If the smallest upper bound is Z star, then Z star has to be the optimal solution for the primal LP, right? So we can define Z star as upper bound of Z. So what we're going to do here is to find some dual linear program that minimizes the upper bound of our objective value, right? So the objective of the dual, we're going to want to minimize the upper bound of the primal objective. Right, if the smallest upper bound on this primal objective is the optimal solution we found, then this has to be the optimal solution, right? Because we can't go any further up because that's the smallest upper bound we have. So here's an example. We have max, the objective function of negative 2x1 plus x2, followed by two constraints and non-negativity constraints for our decision variables. Well, the first thing we're going to do is we want to kind of put this in a generalized format, and most maximizing LP generalization formats are going to be some linear combination on the left side, less than or equal to some value, right? So in this case, we're going to turn this into x2 minus x1 is less than or equal to 1. So we have our two generalized constraints. We're going to add two multipliers, y1 and y2, and we're going to multiply into the constraints and then add them up. All right, so we're going to have y1 of x2 minus x1 plus y2 of x1 plus x2 is less than or equal to y1 plus 5y2. All right, so this is why we put it in generalized format, is because I can take the linear combination of the multipliers and the constraints, and it has to be less than or equal to the multipliers with the constraint on the right-hand side. Well, let's think about this. Remember that we wanted to find an upper bound for our objective value, right? So let's see. Let me rewrite this in terms of x1 and x2. So we're going to have negative x1 plus y2 of x1 plus the y1 plus y2 of x2 is less than or equal to y1 plus 5y2. Okay, so in this dual, remember that we wanted to put an upper bound of our original objective function, which is this, negative 2x1 plus x2, right? So now we have this inequality. Our original objective function is upper bounded by this new objective function of our dual. But, okay, let's think about this. We need to make it so that our constraint because originally we had these coefficients, right? And we don't want to use this objective value in our LP. Then how do we get to negative 1x plus x2 is less than or equal to y1 plus 5y2? Well, we can get it from this side, right? So you see how I rewrote my linear combination of the multipliers and constraints into some form that looks like the objective function, right? So this should be like, this is the coefficient of my x1, and this is the coefficient of my x2. Well, we know that the original objective of the primal is negative 2 and 1. Those are the coefficients. So I want to now make these values, like I want this inequality here to hold, right? I want this objective value here and this linear combination function, this inequality to hold. So for this to hold, I can set y1 plus y2 is greater than or equal to negative 2, and then y1 plus y2 is greater than or equal to 1. Now, by having these two constraints, this inequality up to this point is going to hold, right? And what we're going to do now is that because this inequality holds, then I know this can be an upper bound on my primal objective function. Thus, remember, we wanted to find the smallest upper bound to our objective function, and that is should be the same as our objective, the optimal objective value, right? So let's take this. Let's write my dual LP. So my dual is going to be minimizing the upper bound we have, right? We're going to minimize this upper bound, y1 plus 5y2, and we're going to have constraints. And the two constraints that we have are these constraints, because these two constraints ensures that my upper bounds, like this intermediate expression, that's upper bounded by the upper bound we've defined here, this intermediate expression must also upper bound our objective value. And that's how we ensure that it's through these two constraints. Now we have y2 minus y1 is greater than or equal to negative 2, and y1 plus y2 is greater than or equal to 1. Okay, so don't forget about the non-negativity constraints. So we need our multipliers to be non-negative because these were inequalities, right? If y1 became negative 1, then my inequality is going to flip, and we don't have our original constraints back. We want it, because our upper bound is basically saying that, okay, given these constraints, how can we upper bound our primal objective? Now, if one of these values or both of them became negative, then our constraints change, and that's not going to be able to tell us what the upper bound of our objective function value is subject to the constraints we have originally. So that's why we need the y1 and y2 non-negative constraints, right? So let's say, so let's say we want to solve this linear program. So one way to solve it is to just graph it out and find the two. So let's graph this out. Take the points, right? So we have x1 here, x2 here. So we have the non-negativity constraints over here, and let's graph out my let's graph out my constraints one at a time. So constraint 1 is going to be, let's see, y2 minus 1 plus. So here is going to be negative 1. Our slope is going to be 1. So this is going to be 1. And this is going to be my constraint 1. Right, I'm just rewriting this inequality into slope-intercept form. So we have y2 is equal to 1 minus, let's turn this actually. So if y2 is equal to y1 plus 1, yeah, so actually this should be 1 here. And now we're going to have a slope-intercept of 1 going upwards, and this is my first constraint. And for the second constraint, we have y2 is equal to 5 minus x1. So 2, 3, 4, 5. This is going to be 5 over here. And I'm just going to draw this line out here. Okay, so let's see. In our first constraint, if we are at, let's say this is 1 and 1, 2, 3. 1 and 3. 3 is not less than or equal to 1 plus 1. So we're actually going to have this region and this for our inequality constraint on g of 1. And on this side, we know that 0 and 0, we check whether the origin is less than or equal to 5, which it is. So everything on this side of the origin is going to equal to, it's going to be my feasible region, right? So it's this side plus this side as well. So now I have this feasible region over here, and our extreme points are going to be these 5, right? The linear program, the optimal value in a linear program is going to be the tangent. We can take a contour line of our objective, and it has to be tangent to the extreme point. Otherwise, you can just check all of these and see where it is. But I'm going to actually show where the extreme point would be. So let's see. We have y2. So we have slope of 2 going up. So we have, let's see, we have contour lines like this. Contour lines like this, going in and going in, right? So it's going to be one of these two because they're a tangent. Or we can just check, right? 0, 1. We're gonna get a objective value of 1. Here it's 5 and 0, so our objective value is actually just gonna be -10. So this is my best value, right? So z star is equal to 1, and that's using 0 and 1. Okay, so what if we minimize the dual? If we minimize the dual, we're going to see that, let's see, the dual solution for the dual is also going to be 1, and y1 and y2 are going to be 1 and 0 respectively. So you can grab this out and you'll see that you'll see the same thing. So here we have the optimal y1 star and x1 star and x2 star. Here we have the y1 star and y2 star, right? Now, here's a question. Suppose that constraint 1 became x2 is equal to x1 plus 1. Will optimal objective change? So will the optimal objective change? Right, that's one question. And will the dual change? Okay, now let's take a look at our primal linear program over here. We see that our objective value is 0 and 1, right? Okay, now if our second constraint changes to x2 equals x1 plus 1, like this was originally, so our original feasible region is going to be bigger than the feasible region after changing the constraint, right? Because this is the equality constraint poses a much more restricting area for the feasible region. So we're considering a more relaxed LP and taking it into a more constrained LP. And well, let's look at the optimal decision variables for the more relaxed LP. It's going to be 0 and 1, which, if we can see here, we plug in 0 and 1, like 0 and 1 doesn't change. Right? So what we're saying here is that we're taking the optimal value that we found, the optimal variables that we found in the more relaxed LP is still is not going to be violated. It's not going to violate any constraint when we make that LP more constraining. Then this must also have to be this must be optimal for the more constraining LP. Oh, I am running out of juice. More, let's see, restricting right? This is always the case. I had an original linear program. I found the the optimal objective value and the optimal decision values, and then I took this linear program, made it more constraining. Then, if the original optimal decision values don't change, then it was optimal for a relaxed problem. Then why, like, it has to be optimal for the more constraining problem, right? It does not violate any new constraints. So therefore, the objective does not change. Now, will the dual change? Okay, so remember when I said that we added these non-negativity constraints on the multipliers? Because we didn't want the sign to change, right? But now I went from an inequality to an equality, which means that I no longer care whether the multiplier on y1 is negative or positive. Because if it's negative or positive, it's not going to change this equality, and therefore it's not going to change the constraints on our original primal objective value, which means that we're still going to be trying to upper bounding the best optimal objective here, and subject to these constraints. And like, if I were to take this y1 greater than 0 away, it's not going to change how our constraints function, because I can't, like, there's no flipping this equality sign, right? So the answer is no. The answer is yes, no longer needing y1 is greater than 0.